Yep, they're going to have a little delay for sure.
Come on, we're trying to get our work done
All right. So as I mentioned, today's notes they're pretty quick, okay? But we're still covering some bases for terminology and ideas and concepts that we need to know as we progress through this course, okay? So today what we're going to be looking at are mixtures, defining the various types of mixtures, how can we, what techniques of separation can we use for particular types of mixtures, and so on and so forth. So let's start off early and define what a mixture is. It's a combination of two or more pure substances. We talked about what a pure substance was early on, in which each pure substance retains its individual chemical properties. That's a big statement right there. It retains its individual chemical properties. Now, mixtures can have variable compositions. In fact, they can have variable compositions and infinite combinations. Almost every type of matter that we encounter on Earth is considered to be a mixture. It's very difficult for things to remain pure since naturally substances tend to mix. Oftentimes, certain substances prefer to be part of a mixture than to be itself. In fact, certain elements like sodium, potassium, lithium, okay, you will only find those in nature as part of a compound because of how reactive they are. Some examples of mixtures are salt water and sandy water, and yes, there is a difference between those two. Salt water is simply just going to contain dissolved salt, colorless. It almost looks like it's pure water, okay? But we can separate the salt water mixture through some physical properties. Water boils at a significantly lower temperature than salt does. So we can take that salt solution, heat it up to boiling. That water is going to go from liquid to vapor, and then it's going to leave behind the salt. And that salt, once it's all left behind, is going to have the same chemical properties as it did before it went into the solution. But sandy water is the complete opposite of salt water. Sand is grainy, does not dissolve in water, which is a good thing. Otherwise, we would not have beaches. But we can still separate sandy water, and that's through a different means. We can use filtration. We're going to talk about various methods of separation today as well. So there are two main types of mixtures. The first one we're going to talk about is heterogeneous, or if you want to call it heterogeneous. You're going to hear both ways. Okay. Again, heterogeneous mixture or beginning means different. Okay, it's a mixture that does not blend smoothly throughout, and the individual substances are going to remain distinct. One of the key things we say when we're talking about mixtures is uniformity, meaning the same distribution all throughout that mixture. Well, heterogeneous mixtures are not uniform. Okay? You cannot take drops from various locations of that mixture and have the same ratios of substances. Let's look at the sand and water mixture. If you were to have a glass of sand and water, okay, try as you might stir it up, that sand is still not going to dissolve. And so typically it'll settle out towards the bottom. If you were to take a drop of water or a drop from the top of that sandy water mixture, that drop would contain mostly, if not all, water. But if you were to take a drop and remove that drop from the bottom of that cup of sandy water, that drop is going to contain mostly sand. So the ratio of sand and water is not going to be the same, or the ratio of components of that mixture are not going to be the same throughout. Same with orange juice and the pulp, if you like that type of orange juice. Okay, the pulp will oftentimes float onto the top of the juice, and the juice will stay below. No matter how hard you try, again, you cannot get those two to mix. They will eventually separate. Another example of a similar type or of a type of this mixture would be Italian dressing. Anybody here use Italian dressing? Yeah. You notice that you let Italian dressing sit for not even that long, but maybe a few minutes, it begins to separate out into their usually vinegar and oil. Okay, get those two separated types of substances. And the only way you can really get them together is you got to shake them up real quick, and then you got to put them on your salad. But no matter how hard you shake and mix, it will not stay together. It will not be uniform throughout. The second type of mixtures are homogeneous or homogeneous. These are mixtures that have constant composition throughout and that will only contain a single phase of matter throughout. So whereas we saw in the heterogeneous mixtures with the sandy water, sand was solid, the water was liquid. In homogeneous mixtures or homogeneous mixtures, oftentimes you're going to have two liquids coming together to form liquid. You can have solids, you can have gases as well. So all three states of matter could form homogeneous mixtures. Going back to that salt water example, we dissolve salt into a cup of water. Every drop, no matter where we take it from, it could be from the very top of that water, it could be from the very bottom of that cup, it could be in the middle, or anywhere in between those locations. It will always contain the same relative amount of salt in water. Same with soda. Okay, you could take a sample or a sip from any part of that mixture, and it should have the same relative amounts of sugar, unless it's sugar-free, carbonation, water. These types of mixtures are what we refer to as solutions. We deal with a lot of solutions in chemistry. To give some examples of solid mixtures, we have alloys. Okay, alloys, in terms of other substances, are relatively new to our knowledge and our usefulness. And so, alloy is simply just a mixture of metals. A good example is U.S. Mint's golden dollar coin. This particular coin is considered a solid solution. But look what's funny about this golden dollar coin. Do you see gold anywhere in there? 77% copper, 12% zinc, 7% manganese, and 4% nickel. But this is considered a solution, a solid solution, because we could take pieces or samples from anywhere on that coin, and it will contain these relative percent abundances in every sample I take. So it's uniform throughout. So what happens when we end up having mixtures and we want to separate them out? Well, we're going to talk about a handful of techniques. Okay? As we just mentioned, most matter will exist naturally in the form of mixtures. Mixtures are physically combined. That's a big, important statement. Okay? We're not saying they are chemically combined, but physically combined. If we say that they're chemically combined, then we're going to have a completely new substance. No longer a solution or a mixture. So they are physically combined, and they should be able to be separated out through various physical means. And we do these separation techniques based off of the physical properties of the substances that are mixed together. So it's important to know various properties of the substances that you're dealing with. So the first one, filtration. We've already mentioned filtration once today. But here in filtration, we have a porous barrier, which means it's got little holes to allow certain things to move through. Then this porous barrier is used to separate solids from liquids in heterogeneous mixtures. Again, as we are talking about the separation techniques, we'll also be mentioning what type of mixture it is best used for. In filtration, this is going to allow for the liquid to pass through that porous barrier, leaving behind the solids within that barrier, and that liquid can come through. What is an example of a filtration? Where would you use filtration?
Strainers for like noodles.
Okay, strainers for noodles. Yeah.
I use that all
Yeah. What'd you say?
Piping,
Piping? In what way?
like for a pool, you have different like parts of the piping that it goes off to, and that you can switch.
So like the filter system?
Yeah.
Okay, so the filter system in pools. Okay. There's also one that might be used on a more day-to-day basis. What's that? That's a good one. No one's ever mentioned that before. The heating and cooling system. Yes, each one, your HVAC system uses vents in their units to collect particles. A very good one. But also coffee is a very common one. You or anyone in your household drinks coffee, they use filtration.
I would like to meet my mother and my father.
There you go. So yes, it keeps back the coffee grounds while allowing the liquid to flow through. Another example might be if you have a refrigerator that has a water system in it, or if you have one of those Brita water filters containers. Those use filtration. They have specially engineered, there you go, filters that allow for the filters to essentially capture very tiny particles that could be suspended within the water itself. Your second one is distillation. This uses differences in boiling points of substances. And distillation is typically used for homogeneous mixtures. Okay? What happens is you take the homogeneous mixture, so for instance, like your salt water, and you heat it up. You heat that mixture up until the substance with the lowest boiling point is going to start to boil off and turn into vapor. Well, as that vapor rises out of the container that was getting heated up, it rises into a tube system. I know it's kind of difficult to see in this image here, but it rises to this tube system, goes through here, and around a particular tube where it's traveling through, the gas that is, or the vapor, that tube is being cooled. It could be through cold water tubes that are wrapped around it. Could be through some sort of refrigeration system, just depends on the setup, okay? But what that cold water does, or that cold tube does, is as that hot vapor is coming down that cold tube, the cold water causes the molecules to cool off, which causes them to slow down. When gas molecules slow down, they get closer and closer together. Oftentimes, that results in the water vapor molecules rejoining and reforming liquid water. So that liquid water that has now just been cooled is continuing to move on. As you see, there's a slant in this tube, and it is recollected down into that container down there. So we often use distilled water for experiments. Again, helps remove majority, if not all, of the contaminants that are found within water. Our third process is crystallization, and we use this type of technique, which results in the formation of pure solid particles from a solution containing the dissolved substance. Again, this is going to help separate homogeneous mixtures. And this occurs in what we call a saturated solution, where just a tiny amount of pure substance added will often cause the dissolved substance to come out of the solution. It's really a neat phenomenon to see. When you get what we call a supersaturated, basically, you can't, if you want to talk about sugar, like making sugar water, you may have done this in your lifetime where you've gotten a glass of water, poured sugar in there, and you got to the point where you can no longer dissolve sugar in there. It starts to settle out, okay? Well, at the point to where you really can't dissolve any more sugar, that's what we call saturated solution. And oftentimes, if we were to add just a little bit more of that sugar into that substance, it instantly causes a reaction to where we start to see crystals form. Pretty neat thing to see. But have any of you ever had rock candy before? Okay. I mean, I even had it. I don't even have a sweet tooth, but I mean, as a kid, wow, right? All that is just crystallized sugar that has gone through the same process, either through by placing a wooden dowel or a string into this saturated solution. They provide a surface for the sugar to adhere to and eventually begin to form crystals. And that's where you get rock candy from. Fourth process is sublimation. You go from a solid directly to a gas. You skip the liquid phase altogether. And sublimation is used to separate mixtures of solids where one sublimates and the other does not. Very common substance that does this is dry ice. It goes from solid block to gas, bypasses the liquid phase. And lastly is chromatography. This is a technique that separates the components of a mixture on the basis of tendency or the tendency of each substance to travel across the surface of another material. That's a very lengthy definition there. And really, what happens is when we have a mixture with various components, those components will move at different rates depending on, quote unquote, the size of each component and, the willingness for those larger molecules tends to separate out. Now, this chromatography might be something you've either done in a previous class or maybe you've done it at home, okay? Where you may be given a piece of filter paper. It could be a coffee filter, or it could be an actual piece of filter paper, scientific filter paper. Then you're given a black marker. In that black marker, you place a dot, and then you place that filter into a solution. It could just be simply water, or it could be another type of solution, solvent. That solution will begin to be soaked up by the filter paper and travel upwards. And as it's traveling upwards, it's going to come into contact with that black marker spot. And it will begin to move the various components that make up the black marker further and further up that piece of filter paper to where you get a gradient. It's difficult to see here. You get a gradient of colors, and those colors are what made up that marker. But each one of them has a different rate of movement based upon the tendency to travel up that substance. So that finishes section 3. I am going to stop the recording.